Hello and welcome to Add-on. So today we will learn about the position of Fermi level in case of intrinsic and extrinsic semiconductor. Now before we dive into the answer, let's first understand what the Fermi level is. So the Fermi level, which we will call EF, represents our energy level at which the probability of finding electron is 50% at a given temperature. Now this concept comes from something called as Fermi-Dirac distribution or Fermi-Dirac statistics, which is used to describe the distribution of electrons in a metal. So what happens to electron distribution as the temperature changes? Right. So as the temperature increases, electrons can move to higher energy levels. And the formula for this probability, often called as Fermi-Dirac probability distribution, tells us how electrons are distributed across energy levels. And it looks like this. So f of EF is equals to 1 by e to the power e minus EF divided by kT plus 1. Now here capital E, is the energy level we are looking at, and EF is the Fermi level, and K is the Boltzmann constant, and T is the absolute temperature. Now let's simplify the equation. So we have at E equals to EF, we have 1 by e to the power 0 plus 1, which is equals to 1 by 2. That means halves, which is 50% chance of finding an electron at the Fermi level. This is crucial for understanding how electrons and holes are distributed in a material. So let's first talk about intrinsic semiconductors. So the intrinsic semiconductors are the semiconductors that are pure semiconductors with no added impurities. So in intrinsic semiconductor, we have an equal number of electrons in both the conduction band and the valence band. So where is the Fermi level located? The Fermi level is right in the middle of the band gap. Why? Because it has equal number of electrons in the conduction band and holes in the valence band. This balance places the Fermi level at the center, creating a symmetric distribution of electrons and holes. The Fermi-Dirac function is also symmetric, meaning we have equal chances of finding electrons and holes around the central point here. Now, what happens in case of extrinsic semiconductors? So let's understand this. So extrinsic semiconductors are semiconductors with impurities added, which changes the position of Fermi levels in both the cases. So in N-type semiconductors, we add impurities that provide extra electrons. So with more electrons, the Fermi level moves closer to the conduction band. And this shift indicates there are more electrons available, making it easier for them to enter the conduction band, which is right here, and conduct electricity. On the other hand, we have P-type semiconductors, where we add extra holes in the valence band. So here the Fermi level moves closer to the valence band, and this shift represents an increased concentration of holes, which makes the conduction band possible for electron jump into the valence band. Now let's do a quick recap to see if it all clicks. So in intrinsic semiconductors, the Fermi level is in the middle of the conduction and the valence band. And for extrinsic semiconductors, we have for N-type, it shifts closer to the conduction band, and for P-type, it shifts closer to the valence band. So now you know that how to locate the Fermi levels if you know about the type of semiconductor. Thank you for watching.